Tonight's title, H2O in Paradise. I toyed with a few different titles: hydrogeology of Bermuda, geology of a limestone island. But H2O in Paradise was a bit more fun, and really it's all about water. H2O is a sort of central part of this. And I was lucky enough to spend two periods of my life spanning really the sort of beginning and end of my career. Malcolm covered the Africa bit. And it was my interest in numerical modeling of aquifer systems, which sounds very boring, but that happened to be what I was doing with Southern Water and what the government of Bermuda was looking for in 1983. So that got me ahead of 400 other applicants to take on the role. Paradise bit, well, those of you who've been there or have friends who live or work there will know it's a beautiful island, has a fantastically interesting history, has a unique strategic role in the Western North Atlantic. And for me, it was paradise because every day when I went to work, there was another interesting groundwater puzzle to try to solve. Okay, so we're looking at Bermuda in this slide. We're flying over the capital city, the main commercial and government center, Hamilton. You can see in the center the main port. Every single thing that comes onto the supermarket shelves arrives at that port. You can also see it's very urbanized. At its sort of lowest density level, you'd still call it suburban settlement. Okay, you can see here this sort of five-sided grass mound at Fort Hamilton, one of 77 forts and gun batteries all around the island that made Bermuda the Gibraltar of the West, an impregnable bastion during the Napoleonic Wars and afterwards. Bermuda's always had a very key strategic position in the world and always seems to punch above its weight on the world stage. And it has a beautiful climate and lovely people. And you'll also see in this view down the harbor into the Great Sound, you'll see the island is sort of goes down in a line, but then it curves around on itself, so that by the time you've traveled from the airport at the east end and gone all the way to the Royal Naval Dockyard at the west end, you're going northeast again. Simple way to start. You're pretty much very familiar with this sort of diagram, the water cycle, sort of a descriptive picture of what happens. And what we're interested in hydrogeology is the bit that goes underground. And we're interested in what we can measure. So we can measure rainfall, but we're not interested in the rainfall. We're interested in the net rainfall. So we have to subtract evapotranspiration, which can be calculated from weather station parameters. And then we get this little arrow going down to the water table. That's the recharge or the net rainfall entering the water table. And so you can see this blue line, the water table, and everyone's got a well or a water story, but this is the bit that you find in the well. Typically goes from high to low, and in this example, groundwater flows to the ocean. At least it did with Southern Water, and it does in Bermuda. So what we have here, we've got this nice cycle. It's a conceptual model, and all of the parameters are in there are things we can measure. So to bind it all together, we need a governing equation. The governing equation for fluid flow in a porous medium, for groundwater flow, is Darcy's law, which is this hieroglyphics Q equals KIA, but in plain English, the flow of water is proportional to the permeability times the hydraulic gradient times the cross-sectional area. So now you see through this, we've got a system. We've got inputs, We can plug in outputs, pumping from wells, for example. We've got a way of monitoring the system. We can determine the matrix properties. We have a bounding condition along the coast, sea level. And we have Darcy's law to tie everything together. One last thing before this becomes a numerical model. And I'm not going to talk much about models, but this is what they hired me for. We have to chop it up into small pieces in order to capture all the vagaries. So we discretize the area, we grid it, and we now have a numerical model. I missed out one thing in that whole story, which is what happens when the groundwater reaches the coast. Well, as somebody mentioned to me recently, you have saline intrusion. Seawater is denser than freshwater, so it slides underneath. Freshwater floats on top of seawater like an iceberg. And two gentlemen, Mr. Guyben and Mr. Hertzberg, at the turn of the last century, each came up with the same analysis. It's very simple, based on density of freshwater and density of seawater. To put it simply, if your water table is a foot above sea level, the depth of freshwater will be 40 feet below sea level. So there's a 40-to-1 ratio. And somehow that has to factor into the kind of numerical analysis. And there's a downside to this. It sounds great. You just need a little bit of water table and then you have a lot of fresh water below it. But what if you start tinkering with the water table? For example, pumping. Pumping well draws the water table down. You get what's called a cone of depression around the well, and you get a 40 times greater cone of ascension or upconing. So upconing is the death knell of trying to produce water from a coastal aquifer. And the answer to that is, in short, more wells all pumping at a smaller pumping rate. So in this figure at the top, it's been done wrong. You've got a few wells all pumping at a high pumping rate, and the two on each side have already started pulling up salt water. The one in the middle, it started pulling up a bit. It's not sustainable. So if you go to the bottom, it's called skimming. It's equivalent to sort of slurping the cream off the milk. And this is the way to abstract from a freshwater deposit like this. So going back to our coastal aquifer, I want to now turn it into an island. So I'm going to slide it off to the right, slide another coastal aquifer onto the left, stick them together. Now we've got a tropical island. And the only real reason to point this out is that we have a bit of nomenclature. So if you look at the top surface, the water table is curved. The bottom interface with saline water is also curved. So in cross-section, it looks like a lens. And in island hydrogeology or island water resources terms, everyone cuts to the shorthand and talk about a lens. Now, just going back to the lens, this has all been shown as if it's a sharp interface between fresh and salt water, which is possibly you can pull it off in the lab. In real life, it doesn't happen. What you get is a zone of transition where the salinity grades from fresh to salt. So that transition zone is created because of mechanical dispersion. Any sort of movement sort of blurs that sharp boundary. And the main reasons that occurs is, as you'd expect, we're in the ocean, we get tides. Mid-oceanic tide is 2 tides a day. But there are other factors. So we sort of laugh at the concept of sea level because the sea isn't level. So there are other factors that cause this to fluctuate. If a low pressure zone comes across the whole sea level will rise and groundwater will rise. Another factor I didn't mention, but Bermuda, so the most northern place in the world where coral grows because of the proximity of the Gulf Stream. It's not in the Gulf Stream, but it gets spin-off. And the spin-off isn't consistent. You get warm eddies. So the warm water is lower density, which means sea level rises. And in Bermuda, when you get a combination of a warm eddy and high tide, it's called a king tide. So this figure shows a king tide in King Square, which is the meeting place in St. George's, the west end of the island, where normal plaza became a paddling pool for the day, actually twice a day for a week. And here's something else that happened at exactly the same time. This is in the Bermuda Botanic Gardens. It's well inland, nowhere near the coast. Low-lying, there had been no rain. This isn't rainwater, this is groundwater that rose up out of the ground, matching, with a sort of delayed reaction a few days after the first eddy reached the shores of Bermuda. And right next to it in that avenue of trees is South Road, or South Shore Road, which is one of the three main arteries on the island. It's only about a foot above that groundwater level. So you can see in terms of susceptibility of limestone islands in particular to sea level rise and global warming, you kind of imagine it's something that's going to come in from the coast, but actually the enemy could rise up from within. So this could be a taste of the future. And the transition zone, as you'd expect, is thickest, most disruption nearer the coast and where you have a higher permeability formation. And the whole point of that transition zone is it shrinks our available lens, our available groundwater resources. So where is Bermuda? Well, if you ask the postman, it begins with a B. And this is my Guardian Weekly from a few years ago. First was sent to the Bahamas, then to Barbados, and then, like the last one, it says, missent to B. And I guess you can just fill in the blanks. But Bermuda is not in the Caribbean, which is a common misunderstanding. It's actually about 1,000 miles north of the Caribbean. It's out on its own, and it's isolated. It's 7.5 hours by plane from Heathrow, 600 miles to the nearest point of land in the US, and even further from the ports that supply Bermuda with everything it needs. Tectonically, if we look at the oceanic crust, it's firmly in the oceanic crust part of the North American plate, west of the Mid-Atlantic ridge here, and it's on a volcanic foundation. So there was a volcano here. It's about 2 miles high from the ocean floor to the island. So zooming in on that, we've got two ways of looking at this. The volcano is now eroded in these two pictures. It's now called the Bermuda pedestal, or in terms of the coral growth part, the Bermuda platform. So very vertically exaggerated in the upper part and sort of normal scale in the bottom figure. Where it's been cut off, it's about 250 square miles. It was 3,000 feet high, so that would have made it a Monroe. And it became eroded to about 250 feet below sea level, which roughly matches sea level during the Miocene, which is about 25 million years ago. And over most of the platform, based on seismic profiling, the platform is about 250 feet below sea level, the top of the volcanic rocks. Under the island, it's a bit higher. It's only about 160 feet, and in parts of the island, it's as shallow as 50 feet. And there are some beaches where you can see volcanic sand, which my successor, Sean Davis, who's a geochemist, he's studying that now, and I think it's going to provide some interesting research. And I think this is the clue as to why the island formed in that particular part of the volcano. It's just that's where the rim was higher. And when the limestone part of the geology started to form, it had something to bite on, had something to start growing on. But basically, it's sort of a flat platform, and depending on where sea level is, light can penetrate to it. Coral likes warmth, and it's got the Gulf Stream to provide that, and it likes light. So the whole platform now is covered with coral reefs, absolute delight to snorkel and scuba dive. But if we go back to before Bermuda was discovered and settled, it was an absolute danger. It was a menace to navigation, menace to shipping. It was called the Isle of Devils. And in the 1500s, the sailing ships and their trips across the Atlantic, their explorations avoided it like the plague. So the platform is about 250 square miles. The actual bit where there's land today, 20 square miles. With all of these reefs, and going back to before all the lighthouses and navigation beacons and so on were put all around here, there were many shipwrecks, 300 known shipwrecks. And one in particular is the start of history, if you like, in Bermuda, which is the 1609 voyage of the Sea Venture. The Sea Venture was the flagship of a small fleet heading from England to the Virginia colony, Jamestown. It was paid for by the Virginia Company. It ran into a hurricane. The ships became separated. The admiral of the fleet was in the Sea Venture. The lookout cried, "Breakers ahead." The admiral said, "Go below and scuttle the ship." So being good mariners, they went down, cut a hole in the hull. The ship sank onto the coral reef. So instead of being pounded on the reef for hours and days, it settled and they were able to ride out a storm. And when the storm abated, they looked around and there was Bermuda. And they were able to get off the ship with all their tools, all their supplies, 45 men and 1 dog, made it to land and found on land everything they needed to build 2 more ships, the Patience and the Deliverance, which enabled them to continue their journey 2 years later. So, and this, by the way, is the true, I mean, it's obviously a true story, but it's the basis of Shakespeare's play, The Tempest. The investors in the Virginia Company would have been friends of William Shakespeare. So a colourful start to the island, and it is a very colourful place. There's a rainbow on top of Gibbs Hill Lighthouse, very colourful currency. We've got British and American and Caribbean influences, and you can see the Queen's head here is on the dollar bill. Colourfully painted shop fronts, colourful birds, and the colourful plumage of the Bermuda businessman as he goes about his daily business. Bermuda's biggest industry isn't tourism, it's insurance. It's a big insurance center. So continuing the colourful theme and continuing the theme from those very bright pink shorts, there is a pink theme in Bermuda. The buses are pink. At one time, the telephones were pink before they became mobile phones, and the sand is pink. The sand is pink because it's mostly derived from coral. There are some other carbonate elements in there, but coral is the sort of driver of what goes into the sand. We've got this huge platform with coral growing all around it. Depending on sea level, it will be further out or closer in. And in the coral lives another colorful character, the parrotfish. Parrotfish are found in coral reefs all over the world. They're so named because they have this very interesting dentition, a beak. It's actually a mosaic of interlocking teeth. They're constantly growing, self-sharpening. And the reason they're self-sharpening is because they are constantly grazing on coral. They live on the algae that grow on coral. With every bite, parrotfish consumes one small sand particle of coral, passes through parrotfish, comes out the other end, and it's been calculated that one parrotfish produces 250 grams of sand, coral sand per day. It's astounding, but it's true. And I've put up on the slide a rough calculation, and given the amount of time that the platform has been there, the amount of time that coral reefs would have been growing, a reasonable density of parrotfish per square mile, you can account for all the limestone in Bermuda through what comes out the back end of a parrotfish. And as you lie on the pink beach, basking in the sun, you may want to put out of your mind the fact that you're lying on a bed of parrotfish poop. So the water brought this up to the beach, a lovely pink beach. Once it's on the beach, under the right conditions, it will start to blow in the wind. That nasty feeling when you get sand blown. Well, during high sea levels, that was the period when conditions were optimal for sand dune formation. And that's basically what happened. The whole thing became a sand dune machine. And once that engine had everything in the right place, wind in the right direction, corals growing, parrotfish eating the coral, winds blowing on shore, dune formation started. It was observed historically. We've got this very nice watercolor from the National Museum. It was seen by the Challenger expedition in the 1870s, the world's first oceanographic expedition, where they didn't quite know what to call them. They referred to them as sand glaciers because they're moving slowly and they were made of sand. And the sort of Goldilocks zone, I mean, sand dunes will grow. The highest sand dunes in the world are over a mile high. So when the machine starts creating, there's nothing to stop it except vegetation. So what limits the height of a sand dune is vegetation growth, which acts as a windbreak. So Bermuda sand dunes didn't get that high. And once they were in place and stabilized, then rainwater did what it does in carbonate environments. And we know from living in the Cotswolds what happens. Limestone gets calcium carbonate, gets slightly dissolved, and then it becomes reprecipitated. And when that happens within sediment, it starts to stick it all together. So that's what happened during high sea level periods. But we know during the Pleistocene, during that long succession of ice ages, sea level was lower. What happened during that period? There was no dune formation. The areas where sand was being generated were too far from the island. Instead, soils formed, paleosoils, and these formed from, every now and then in the weather report, you'll hear that there's a dust storm from the Sahara that's affecting sunsets. Well, that dust eventually settles. And if you multiply that by hundreds of thousands of years, and there's nothing else being deposited, you'll get a paleosoil. And it's a terra rossa type soil, high in iron. And this was sort of important in terms of the scientific study of Bermuda's geology, because if you look at this slide, if you look above and below the paleosoil, there's two white limestones. They look exactly the same, and in geologic terms, they're not mappable units. You can't trace one from one road cutting to the next, whereas the paleosoils are very mappable and very consistent. and they're datable. And I believe there was a society talk about this, amino acid racemization of snail shells. So the soils had a snail fauna, they can be dated, and through that, you can date the limestone above and below. So the real stratigraphic markers are these soils, but the units that form the aquifers and the sort of named formations are the limestones. So I talked about my successor, Sean. My predecessor, Mark Rowe, together with Len Basher and Peter Garrett, did a fantastic job back in the 70s of creating a geologic map of the island, pulling all of this dating, etc. together. And they came up with 6 different formations shown here. What we're going to do in this talk is simplify that. But first, just to sum it up, we talked about high and low sea levels. Here's how high and low sea levels looked during the Pleistocene. So we're looking at a lot of changes. So in terms of the dune formation at high sea level, the blue line is the present sea level. And you could probably pick out 7, 8, or 9, it depends how picky you are, highs that would have matched something like the present day coastline. I've put in here the top of the volcano. This is the 250-foot deep mark. So we're not really worried about anything that happens below there. If sea level is down, that means the whole platform was high and dry and soils were being formed, but no sand dunes. And so for our purposes, we'll just split those 6 or 7 formations into 3. The oldest, we call the oldest, older, and young. So, and this is in hundreds of thousands of years. So roughly young is about 100,000 years old. Older is about 200,000 to 300,000, and oldest is about 400,000 to about 2.5 million. Dune formation in the high water levels, paleosol formation in the lows, and then something that's quite important in Bermuda, cave formation. Caves form above the water level. So when sea level is down and you've got this mass of limestone, caves can start forming. The whole process of dissolution and reprecipitation, the cave forming engine can start. And so on our simplified map, I've now got young, older, and oldest. It's a bit like the 3 bears. And if you imagine Bermuda as sort of a line, you can see a bit of symmetry. There's a sort of central axis. The oldest rocks, roughly, are in the middle. The ones that are slightly older, slightly younger, wrap around them. And then the youngest rocks are on the north and south shores. And I'll show you the how we can tell the paleo wind direction. But in every case, as you would expect, paleo wind direction is onshore. You can only really see it in the young limestones. So I've already talked about carbonate dissolution, reprecipitation. You do that over hundreds of thousands of years, the rock changes, and every process that changes a rock from deposition of the sediment up to metamorphosis is called diagenesis. And horrible Greek word, but I'm just going to illustrate it now with pictures. So the youngest rocks look just like the beach. You would be mistaken for thinking this was the beach sand. The carbonate sediment that's holding all this together is right on the point-to-point contact of the grains. It's halfway between rock and non-rock. You go one stage further, so we're now in the 200,000-year-old stage. After all that interaction with percolating rainwater, you can see all the minerals have changed. Calcium carbonate has changed its form from aragonite to calcite. And you can also see the development of these little holes, which I've brought a sample here all the way from Bermuda. You see these little, what we call macropores or secondary porosity starting to develop. So we add another couple of 100,000 years, and now the rock is completely solid mineral. It's incredibly hard, but with some very big solution enhanced openings in it. So we can think of it also in terms of, we're going to go on to permeability. We've sort of gone from a drinking straw to a fire hose, and this affects what happens with groundwater. So we see the same pictures again. The graph in the top right shows roughly the order of magnitude of the permeability of these three different ages, going from 50 meters a day in the youngest rocks to about 5,000 in the oldest rocks. So if we go back to that transition zone, the thing that eats away at the bottom of the lens, and you remember I mentioned that transition zone is thickest in the more permeable rocks. The young rocks, being the lowest permeability, have the thinnest transition zone. That's where we find the thickest groundwater lens. So that is sort of the groundwater resources part of Bermuda's geology. As you get older, permeability increases, the transition zone gets thicker, the lens, if there was one, would get thinner. Eventually you end up with the oldest rocks, which are no lens, useless as a groundwater resource, good as a building stone, but with two other really useful properties, if you like. In some cases, the solution has created spectacular caves, show caves, that are tremendous for tourism. Also, the network of caves under the island is so unusual that there are some very isolated caves in which unique species occur. Basically, they're endangered species such that not only are they only found in Bermuda, in some cases they are only found in one particular cave. And these are blind albino cave shrimp. Bermuda has to comply with all the international treaties that Britain has to comply with, and one of them is protection of endangered species. So these cave shrimp are quite high on the environmental protection list. Here's what these rocks look like in outcrop, and this is one of the young rocks. You can see on top, looking at a sand dune being developed, these would be the top set beds, the flat beds that push up as the sand rolls along the top of the dune. And these are the foreset beds. This is where the sand is rolling down the downwind slope of the sand dune. So paleo wind direction is very clear and easy to map. Go back a couple of 100,000 years, and you can just about make out the bedding still there. You can see that the primary porosity is gone, but this secondary porosity, these bigger holes, is starting to develop. And then we get into the good stuff, the oldest rocks, some fantastic looking caves. This is the Crystal Cave, great tourist attraction. So I mentioned that caves only form above the water table or above water level. And looking down from the walkway, you're looking down into a cave, so clearly that lower part of the cave formed when the water level was lower. The question is, how deep does it go? Somebody went to answer that question. In 2011, there was a project called Deep Dive Bermuda, and one of our colleagues, Tom Iliff, was part of it. And they took part in the deepest scuba dives ever attempted, going as deep as over 600 feet, breathing 50% helium. And here at 210 feet below sea level, they found a limestone cave. If you remember, the top of the volcano is at 250. This cave is at 210. So it's just above the top of the volcano. So having looked at sea level changes, having seen the caves that we can see right at ground surface, it's not a big stretch of the imagination to say that there probably are caves that go right through the island. So, got a very porous limestone, rainfall just sinks right in. How are we going to get our water? There's plenty of rain in Bermuda. There's about 6 feet of rain per year. It's fairly evenly spread through the months. But there's no fresh water lakes, streams. The only surface water really that matters is when there's a flash flood. When it does rain, it rains heavily. Flash flood on the roads. And this will become part of the story. That water gets channeled to drains and soakaways, goes back into the limestone. So everything goes into the limestone somehow or other. So how do you get your water? The answer is you catch it on your roof. So the early settlers, even roofs made from palmetto leaves, they found a way to catch the rain that ran off it. And being sailors, remember they crash landed on the island, they were used to barrels. So they built barrel-shaped vaulted tanks. And that tradition continues. And in Bermuda, they've got a very interesting attitude when it rains. Everyone sort of looks at each other and smiles and says, tank rain, because it means you're building up your water supply. And this is the primary source of water for everyone in Bermuda. It started as a necessity, and then it became sort of set in law. So under the public health regulations and the building codes, by law, you have to catch water on your roof. You have to have these little tracks called glides on your roof, and they lead to pipes that go below the house to a tank. So that's how it looks. And then below the tank, below the house, by law again, you have to have a tank. 10 gallons per square foot of roof, dictated by law, and that's equivalent to catching about 4 months of rainfall. So you've got 4 months rainfall in reserve in your tank in an average year. So it adds a little bit of expense to building, but the Bermudian psychology is liking to be self-sufficient, liking to being sort of in control of your own destiny. So to see if this is, to see how much water that translates into per person, to get a sort of metric. What we did for this graph was we went back through roughly 60 years of data, calculated the roof area by decade, looked at all the rainfall statistics and multiplied by 80%, and then calculated what the catch would have been. And on the left, you'll see millions of gallons per day averaged out over the year. So we're looking at about between 2 and 3 million gallons across the island. And on the right, which ties in with this blue line, it's the average potable water per person per day. And roughly about 40 gallons per person per day. It sounds good because British average is about 25 to 30 gallons per day, potable water use. But you'll see it's very variable. I said on average, it's about 6 feet of rain per year, but some years are dry, some are less dry. And you've only got 4 months storage in your tank. So Bermudians are can be very stingy, very aware of how much water is landing, and very conservative when it comes to water use. And it's a hot island. So if you'd like to be clean and you'd like to do your laundry regularly, this may not be enough. So what developed on the island was a network of small companies, water truckers. Very simply, they take water from where it's abundant, say a church or a hall. Every building has to have a roof catch and a tank, and take it to where there's less, where there's a need. But it's expensive. You've gone from fairly cheap catching your water on the roof to a really, probably the most expensive way of bringing water to your house. Therefore, people became very interested in groundwater. When I arrived on the island in 1983, there were 3,000 small domestic wells on the island. And I believe 3 drilling companies. And there was a lot of data to suggest that some areas you could drill for water. It's always at or near sea level because the water table doesn't build up that high. It's only about, maximum height is about 1 foot above sea level, which matches our 40 feet freshwater below sea level. So it was known that water was available, but it wasn't really understood how you could predict what quality it would be. It was in some places it was fresh, some places it was brackish, some places it was saline. Obviously, it did depend on, in a big part, on how deep your well was and how fast you were pumping. This was not all well understood. It was a sort of an empirical trial and error technique. And so the government decided to get involved in the water business, started to put in wells for public supply. A private company, Bermuda Waterworks, also started up. And the next stage really was to start a scientific analysis and evaluation. Where is the fresh water? So this took place at the same time as the big mapping exercise. And 4 main areas of freshwater lenses were defined. The main one being the central lens in the middle. It's larger, thicker. It's considered freshwater. You can pump it without upconing. The thinner ones, Somerset, Port Royal, and St. George's, it's hard to pump them without getting a little bit of saline upconing happening. So they are really considered brackish water resources. It can be pumped, but that water will need to be desalinated. Also, at the same time as defining the lenses, a monitoring well network was put in so that whatever happened in the future, the lenses' thickness and size could be tracked. And the big question was, and kind of why I was brought in and why numerical modeling became a big issue, was what is the safe yield? How much can we really pump? How do we do it without getting upconing? All of these questions you can't answer qualitatively. You have to have some sort of quantitative way to do it, which takes us back to that water cycle. Starting with rainwater, catching the water on the roof. If we're going to calculate the water resources, we've got to figure out what's happening to that roof water. And if you look at the degree of urbanization, and this is probably the most extreme, the city of Hamilton, just about every square inch of every block is either a roof catch or an impermeable surface of some kind, which somehow or other is catching water. We'll skip through the middle part. Let's just say that water all gets into the aquifer. Here's St. George's, the old capital, switched from St. George's to Hamilton in the 1700s. Again, lots and lots of roof catches. Painted white because you want your water to be clean. Oh, and also in here you can see King Square, normal water level, not outside of a king tide. So, together with Stephen Foster from the British Geological Survey, back in the 80s, we started thinking about this in a little more detail, and we realized that the effect of the roof catches was really huge in terms of Bermuda's groundwater resources. If you just look at rainfall landing on naturally vegetated area, this blue bar shows you get about 25% of that rainfall becomes recharge, gets down to the aquifer. If you go to a typically developed area with a lot more roof catch and road catch, you almost double the amount of recharge. So that's significant. We've sort of gone from, it's like doubling the rainfall on the island by building a house. And it's kind of fun. Back in those days, we were writing our own software programs, we were writing our own aquifer models in Fortran. We also did our own recharge mapping with scale rulers, detailed maps, measuring off each little block of a roof or a road, and very laboriously pulling all that together to create an input to a model. Now we could do it by color. So on this aerial view of Bermuda, green vegetated would be 25% of rainfall, white roof catches, and you can see the degree of development. It's a very urbanized island. That's going to increase it to 50% or more, depending on the building density. And with GIS, you could analyze this photograph and you could contour recharge on a very fine grid. And the same gray road surfaces, you could do it so easily, as I was just discussing. But we did it the laborious way and ended up with a model. And you can tell the age of the model from the graphics. Today, you can go to OnFlow or FeeFlow or AquaChem or CWatt, and you can pay a couple of £1,000 or dollars and buy a package that will do all of this for you. In those days, you had to write your own code. The code that I wrote for Bermuda was adopted by the United Nations Department of Technical Cooperation and Development for use in small oceanic islands, but its target audience was Bermuda. I'm not going to go over everything in here. It's a feature-rich slide, but you can see roughly, I've chopped off bits of the island, so it just shows the part of the island that contains the central lens. I've got a couple of water table contours, which are the kind of decision points for whether this works or not. And this is a paper in Groundwater Journal. And by basically trial and error modeling rather than trial and error drilling and pumping, I was able to predict that we could increase the amount of groundwater that was being abstracted from the lens safely from about double. So from about 1 million gallons a day at that time to almost 2 million gallons a day. And knowing from some of the work that I had already done with Stephen Foster, we knew that that was going to affect water quality. We were going to bring in higher nitrate water and some additional saline water so that desalination, which was sort of in its infancy, would need to grow. So we would need a combination of pumping from the lens and treatment. And I should make it clear that a lot of people live over this resource. It's not a pristine, bubbling Rocky Mountain spring. It is affected by the people living there, as you'd expect. Water's the universal solvent. So additional desalination needed. And let's see if that prediction came true. I had said we would move from about 1 to 1.8 million. So on the scale on the left, we've got million gallons per day. And we've got two blocks on the graph. The blue is the private water company, Bermuda Waterworks Limited, and maroon is the Bermuda government. You can see the Bermuda government really stepped up its game once it had completed that scientific assessment in the 70s. So by 1986, which was roughly when this study was being done, they were pumping $1 million. 16 years later, 1.8. So I think the model was good. And the monitoring of the lens showed there had been no derogation. It was coping with the additional abstraction. So you would think we could rest on our laurels at this point, but if you look at the rest of the graph, you'll see something happened, and I shall explain why groundwater use in Bermuda from that peak then started to go down quite dramatically. And we'll start off with seawater reverse osmosis. It really started to become more efficient in the beginning of the 1990s. And that's a big part of the tail. But another big part of the tail is just managing this system. The model had depicted the amount of recharge, the safe yield, and it was able to break it down into sectors. So each of these little colored blobs on this map is a sector that had a number of gallons per day permitted abstraction. Monitoring well network to keep track of whether that was good or bad. But if you look at the big block of wordy text at the bottom, the big takeaway is there are 274 abstraction points. I mentioned that it was a private water company and a government water section. Now, the private water company, if I flip back, you'll see that their abstraction really continued quite level. And it was the governments that dropped down. And the reason is private industry were able to buy land. They could put their wells off the road. Government couldn't. The way land tenure works in Bermuda, the government doesn't get much say in it. And the government didn't have a lot of money to buy land. So when they started building up this water development system, pretty much all the wells were put in roads. So if you have a block of wells in a road, you need to work on 1 out of, say, 10 wells. You have to stop traffic. It's very disruptive, and you have to pay to reinstate the road. This approach started to look a lot better. What we're seeing here is 3 different desalination plants. And if you add up the total gallons per day, we're looking at almost 1.8 million gallons a day from 3 plants, as opposed to 374 abstraction points. 1 pipe in, 1 pipe out, air conditioned, easy to park, no drivers yelling at you. It's pretty obvious why the government's water section decided this would be a better route to take. So desalination had become cheaper, and it was clearly way easier to run. So let's put that back onto our graph of the roof catch. So we've got our 40 gallon per day marker. Now I've added in potable water produced from groundwater resources, and then I've added a couple of layers on top of that, potable water produced from seawater desalination. So from 40 gallons a day roof catch, we're now up at about 60. The whole island is starting to look a lot more sustainable. And at the same time, of course, distribution systems were starting to grow, pipelines going out across the island so that you can have a roof catch, a tank, and a pipe with a meter coming to your house. I previously mentioned 3,000 small private domestic wells. By law in Bermuda, you're not allowed to use a domestic well for potable water. You can't plumb it straight into your tank, but you can use it for non-potable purposes like flushing, which means you don't have to use potable water to do that. So effectively, you've increased your potable water supply. And so this extra layer on top is the calculated additional non-potable supply, having your own backyard well. So now we've gone up from 60 to 75 gallons per day. Water security through this sort of kaleidoscope of different systems is becoming much more of a reality. So I skipped out the middle part. How does water get from your roof back into the aquifer? So if catching water on your roof was the traditional way of getting your water supply, this is the traditional way of getting rid of your wastewater. A hole in the ground. And in fact, when this was introduced, this precast soak-away pit, this was a great innovation because literally a hole in the ground had been the way most homes disposed of their wastewater. I did warn you that this isn't a pristine aquifer. It's what you'd call a raw water source for treatment. However, even if you have just a soak-away pit, under Bermuda conditions, you do get some mitigation. First of all, it's warm, bacterial activity is higher. A near-surface pit, because it's a porous rock, does have a lot of air. So there is some aerobic digestion that takes place just within that first 3 feet. It's a fine sand, so you get sand filtration, which is the standard first approach in wastewater treatment. And interestingly, if you're concerned about detergents, phosphates getting down into the groundwater, phosphate doesn't get anywhere because it reacts with calcium carbonate in the limestone, forms calcium phosphate, and stays put. We did a back of the envelope calculation. We calculated that 1 foot of limestone below a soak-away pit has enough buffering capacity to absorb a century's wastewater disposal. One thing that doesn't get stopped, though, is nitrate, a very key part of sewage. So going back to the Thompson and Foster study, I sallied forth, and on this map you'll see all the wells that I sampled over a 1-year period and had analyzed for nitrate. And we found a lot of interesting things, but the main thing was that you could almost map population density by nitrate concentration in groundwater. Not really a surprise. So I'll just go back and say, untreated groundwater is not for drinking in Bermuda. It's not potable. There were some wells where we found fecal coliforms, and consistently, that was where the thickness of limestone above the water table was less than 10 feet. And from that came a definition of a water resources protection area. So the hydrogeologist has 2 heads to comply with under planning. One is cave protection, the other is water resources planning area protection. And the 10-foot rule became part of defining water resources for planning purposes. If you look at the middle of this figure, you'll see 40 milligrams per liter as nitrogen. Nitrate, the World Health Organization standard is 10. If you drink water, if pregnant women or babies drink water, you will get blue baby syndrome because of the extra nitrate. So it's a health problem. Looking at the raw water from the government supply, nitrate concentration over the years, trend was clearly going up. because it was expanding into more heavily populated areas. There's the WHO standard. So already by the 1970s, government was having to blend fresh groundwater, if you like, still went through disinfection, but had to blend that with desalinated water to get below 10. So it wasn't really a big stretch of my forecasting power to say you will need more desalination, because both salinity and nitrate were pointing in that direction. We're now going to go deep. So looking at this cross-section, a sort of cartoon cross-section, you'll see the lens is sort of high up. The bit that we're protecting water resources is high up, but we've got all this stuff below it, which is very permeable. And rather than run a pipe to the sea and kind of spoil marine water or beaches by piping stuff you want to get rid of to a beach, why not put it underground? And under the Bermuda Water Resources Act, this was allowable, it was being done. It did have to be sort of formalized in a protective way, but there's lots of, this is a great resource, having somewhere to get rid of your wastewater. So reverse osmosis concentrate, you know, you're creating fresh water, but you end up with a brine, got to get rid of that somewhere. Treated sewage effluent, laundry wastewater, much easier to get rid of if you just send it downwards. But it has to be done in a way that protects the water resources above. So the concept came up of a deep sealed borehole. The idea is that you seal through the upper part of the resource and go into an area where it's not a problem. And the deep seal borehole concept started in the 1970s and continued, and the concept is pretty simple. You must seal your borehole, your disposal borehole, to at least 40 feet below the water table. And here's how you do it. So going from left to right, you drill a hole. It's a rock, so the hole stays open, it doesn't collapse. You insert a pipe or a casing, plastic, because it doesn't rust. And then there's an annulus around that pipe into which you can pour cement to form a seal. You seal it all the way up to the surface. Then when it's set, you go back down through the middle and drill into your disposal zone. So this all looks great, except we have the water table. So if we just pour cement in, gravity doesn't really work the same when you're below water. Archimedes' principle does something. And the approach is pretty simple. It's an engineering construction technique called tremming. So you put a narrow diameter pipe down the annulus, pump the cement in under pressure. And when you see the cement arrive at the top, you know you've got a good seal. And you carry on. The 40-foot minimum, by the way, is a minimum. And depending on the amount of water, site conditions, a lot of other factors, it can be as high as, the highest I ever specified was 120 for extra protection. Oops. So now we come to the last little wrinkle in the story, which is the caves. We're happily discharging water down into these deep zones, but we're required to protect caves. So let's start with a simple bit. Just in terms of controlling development on the island, you have to take special precautions if you're over or near or potentially affecting a cave. It's number one on the planning list of protection zones. So with input from the hydrogeologist, cave protection zones were defined, and they are based on geology. You've already seen the older formations are the ones that have cave development. Mapped cave entrances. So within each cave protection boundary, there are known caves. There's about 180 with known names. depths, conditions, and risks. And then beyond the entrances, there's a tremendous group of cave divers in Bermuda who went down, mapped individual caves. This is just a sample. There's a lot more. So we can now protect almost to the foot where there's at least a diveable cave. So through the planning process, in a strange way that I haven't seen anywhere else, the hydrogeologist evaluates the architect's designs, and typically, if it's over a cave area, requires the developer to have a test drilling and a borehole inspection with a downhole camera before anything can proceed on that site. So that sounds like it's all wrapped up. Well, it isn't, because the best laid plans don't always work, and caves may crop out at any time. So there's 3 pictures here showing work that was approved, yet a cave was discovered. The one I like best is this one showing the swimming pool. The cave appeared when the last bucket of earth was being removed from the excavation. The other 2 pictures show members of the Department of Environment going in, testing for fauna, rare species, and just seeing if there's anything valuable once the cave's been discovered. Here's a fantastic example of the extreme to which caves are protected in Bermuda. So we're now looking at an aerial view of a quarry. This is in that oldest limestone, really good roadstone. Very deep. You can count the benches, the 7 10-foot benches, so it's 70 foot deep. But you'll notice there's a strange little blob of trees down in the corner. What is it? It is a cave. So it was a known cave. The cave entrance is now right at the top of this 70-foot high pinnacle. The quarry was allowed to excavate all around it. And for 20 years, that cave was protected. It turns out it wasn't a particularly good cave. There were no endangered species in it. It didn't really contain any nice stalagmites or stalactites. And after that period of time, it just started to fall apart. And at that point, safety trumped cave protection. So this may be the last photograph anyone took of that cave. Caves, it turns out, aren't very structurally sound once you've removed everything around them. So I'll finish up by giving a little case history where we have some hands-on stuff. So this was a development that was proposed in 2018, a beautiful high-end hotel, condo, restaurant, marina development. It had been a US base, lots of hydrocarbon pollution, which you find on every military base. So this was a great way to turn that brownfield site round into something that was going to be bringing lots of economic benefits to this part of the island. This is out on the west end. Being a big development, it needed wastewater disposal, all the things we talked about, brine disposal, heated water disposal from ground source heat pumps. So all needing disposal wells and double everything for 100% redundancy, and it's in a cave protection area. Here's the cave protection area, and the sort of the central bay was where this whole development was taking place. And it turned out there was no precedent. We had never had to prescribe what was going to happen with disposal wells in this environment. We just avoided it. But this was sort of essential for the island's economy to make this thing go ahead. We knew from the studies of the US pollution, you can see the core here has got lots of vugs and voids in it. The borehole logs show voids, no real evidence of a big beautiful cave, but certainly highly porous rock. So our concern here was that if we used the technique that we talked about before, we pump our cement in, but there would be enough voids that instead of that cement coming back up to the top, it would go down to the bottom. So we would have done three bad things. We'd have wasted money on a well, polluted a cave, and if this was operated, all the wastewater would go back up to the surface, exactly where you don't want it. A gentleman called Carl Keller in New Mexico, he formed a company called Flute, Flexible Liner Underground Technology. And when I was first aware of Carl, what they were doing was using this liner as a tool to do sort of very high-end but researchy type investigations. They were looking at pressure variation with depth, permeability variation with depth, mapping contaminant plumes vertically, with little samplers put on this tube. And what they would do was they would put this flexible liner down with all these instrumentation attached, take the measurements and pull it back up again. So it went in and came back out. My question to Carl, this is now almost 30 years later, should we put in a permanent installation and would it be able to go through a cave? He said, yes, we've written several papers on this. We've been doing it for years. We've just gone through a 9-foot mine opening in Pennsylvania, came out the other side and sealed that off. So I thought, well, this is good. I think we have the answer. Let's start outreach. So we started an outreach program talking to the developers who were going to have to pay for this, the drillers who were going to have to install it. We showed them scientific papers, YouTube videos, but the best demonstration of what we wanted to do was the sock analogy. So you've seen the Bermuda shorts. They come with Bermuda socks. So we attach a sock to the top of a cardboard tube, start to push it in. When you've pushed it in all the way, you've got a liner. So this was quite popular when I took it around, but there was much more to it than this. So after about a year, getting everyone on board, getting buy-in from all the stakeholders, we were ready to deploy. So here's the project site. There are 2 disposal wells going to go in here. And I want to introduce you to the team. The key man in the middle is Cyril Rayner, comes from a long family of well drillers. At the time of this job, he was 93. And I heard recently, he's now 96, still going strong, but starting to slow down a little bit. And with him his cousin and his son-in-law. That's the team, and myself and Jeff Smith, environmental engineer. So here's how it goes in. You start off with the surface casing, the white pipe that's sticking out at the top. That only goes in a few feet. You can see the liner on a reel. Black liner. It's the same material as this briefcase. Heavy duty ballistic nylon. You attach it to the top. So it's the right way round at this point. You put in a breather tube so that as it goes down, any air that's in the well has somewhere to go. And what drives it is very simple, 1 bucket of water. It's so slippery, so little friction that all you need is the load of about 5 gallons of water, and it will start to go down, and you can just use your hands as a brake. So here's Cyril just about to start the whole thing off, looking very skeptical. And as he said to me, we've never done this before. I think you can see that in his expression. But the bucket went in, it started to go down. Once you get to the water table, things change a little bit because you've got to push it down below water. You've also got to get rid of that last little bit of air. So there's another tube at the bottom, the lower vent tube. And we're now lowering that last tail end on a bit of rope. And very simply, what you do is you just pour water in. So we have a hose pouring it in. And what we're all doing is listening to a water level sounder, which is the red reel, the white tape. And when that beeps, you can stop pouring water in because there's enough. When it stops beeping, you turn the hose on again. You don't want to have so much pressure that the thing runs away with you. But it's really great, just hand power to put it in. And there it is, target depth, successfully done, ready for the final touch. So I think it's a success. We did it right the first time. We didn't have to bring in engineers from overseas. We were self-sufficient, which on an island is what you want. Honored the cave protection policy, solved that problem, new technology to use again. And we went from Cyril saying to me, we've never done this before, to that was easy, when's the next one? So that's it. I'm sorry I ran over. I've squeezed 40 years of work into a little bit over an hour. So questions if we have time.
Thank you. Yes.
I wonder if anybody's done a prediction about global warming and how that will affect rainfall and sea level and how it will therefore affect Bermuda and the water problem.
Okay, for the people on Zoom, the question is, with global warming and the effect on changing rainfall, will that affect Bermuda's water problem? I'm not really an expert on the global warming bit, but I do know it will lead to more rain. I mean, we're seeing that in Britain right now, more flooding. I think in Bermuda's case, it means the lens will continue to get bigger, especially if it's not really being drawn from as much as it used to be. But I would say the biggest issue with global warming is sea level rise and sea level warming, particularly as sea level warming affects coral health. Because in Bermuda's case, it's existential. The reefs not only kept enemies away during the Napoleonic Wars, but today they perform the function of breaking the waves before they hit the shore. I mean, it's a physical defense of the island. So coral bleaching and coral death are being seen in lots of places around the world. Global warming is going to make that worse, and it's a very serious issue for Bermuda.
Just as a follow-up, is the tank water drinkable?
Yes. The question was, is tank water drinkable? And the answer is yes, absolutely. It's beautiful. I mean, it's fresh rainwater. If the tank is kept clean and the roof is kept clean, and Bermudians take great pride in keeping their roofs sparkling white, which also has a cooling effect on the house. It's good. It's good stuff.
Yes.
Is ground probing radar any relevance to it?
So I'll answer the question. The question was ground probing radar. Is it helpful, particularly looking for caves? It has been used in Bermuda. It's more useful for things like shallow, say, abandoned fuel tanks. If you're trying to find where it is, you're not really sure. It's one technique. In terms of caves, vertical resistivity sounding is the way to go. There's a company in Florida called Ocean Earth Sciences that's done quite a lot of, covered quite a lot of areas. They actually did part of that Morgan's Point development. Helps you see caves without having to drill into them. So geophysics is useful, but ground penetrating radars are a little bit limited because it's too shallow.
What's the impact of tourists to the island and the sewage system?
What's the impact of tourists on the island? Well, for a long time, it was the primary industry on the island, really important. part of that decline that you saw in one of the graphs, which I didn't pick on, but there was a big decline in water delivery after 2008, year of the global financial crisis. And following that, it hit Bermuda very hard economically. Lots of hotels, there used to be scores of hotels on the island, and many of them shut up shop, changed to becoming residential or condos. So tourism is very important for the economy, and it was sort of the water supply, really, the piped water supply, when that started, it was for the tourist industry. It was started by Bermuda Waterworks to supply hotels. They started that in the 1930s. And when government got involved in the 1960s, that was to sort of broaden the water supply to the wider population. One of the oldest tourists in Bermuda was Mark Twain. It was his second home. And he is on record as saying very succinctly, "You can go to heaven when you die if you want, but I'll stay in Bermuda." It goes back a long way. Richard.
The question from Robin Thompson on the Zoom link.
He's related to
He
me.
says, as potable water demand goes hand in hand with population, are there any brakes on Bermuda's population growth?
That's a very good question from my brother Robin. And the answer is pretty simple. I would say Bermuda's population in this modern era is controlled by economics.
If it's perched on a volcano, is it safe from the Canary Islands tsunami? Should it ever materialize?
That's a good question. I think that's two questions in one. Bermuda's on a volcano. Canary Islands are on a volcano. And there's been a fear that let me get this right, if the magma chamber under the Canary Islands was to collapse, it would cause a tsunami, which would affect all of the North Atlantic, really. That would definitely affect Bermuda. But Bermuda's volcano is very stable. It's sort of been used as a sea level gauge because it's so stable. There are occasionally small level earthquakes on the platform or just off the sides, but really nothing you would write home about. It might, shake your coffee a little bit. But yes, luckily Bermuda's not in the same situation as the Canary Islands.
Any more questions? Thank you very, very much.
Thank you, Malcolm.